Hi friends, welcome back to Acharya Gurukulam. Today's topic is support vector missions, a solved example. In this video, I'm going to explain introduction to support vector missions, terminology, mathematical background, and a solved example. Support vector missions. A support vector mission is a powerful machine learning algorithm widely used for binary and multi-class classification, also for regression problems. SVM is best suited for classification tasks. The main idea behind SVM is to find out the optimal hyperplane that separates different classes or approximates the regression function with maximum margin. This hyperplane is positioned to maximize the distance between the nearest data points of different classes known as support vectors. By maximize the margin, SVMs aim to improve the model's generalization ability and reduce the risks of overfitting. The objective is to find out the hyperplane that maximizes the margin between classes while minimizing classification errors. SVR. SVR denotes support vector regression. It shifts to fitting as many data points as possible within a specified margin while minimizing the margin violation. Types of support vector missions. There are two types of support vector missions. One is linear support vector missions and other one is nonlinear support vector missions. Linear support vector missions is used for linearly separable data, which means if a data can be classified into two classes by using a single straight line. Here you can see a linear SVM. We have two clusters and these two clusters are separated by a linear straight line. But whereas in case of nonlinear, it is not like that. Nonlinear SVM is used for nonlinearly separated data, which means if the data set cannot be classified by using a straight line. Here, the data points can be separated using a nonlinear SVM. The terminology that we used in support vector missions is as follows. Hyperplane. It is a decision boundary used to separate data points of different classes in a feature space. For linear classification, this is the linear equation represented as Wx plus b equal to 0. Support vectors. These are the closest data points to the hyperplane and are critical in determining the hyperplane and the margin in SVM. Margin. It refers to the distance between the support vector and the hyperplane. The primary goal of the SVM algorithm is used to maximize this margin, as wider margin typical results in better classification performance. Hard margin. It refers to the maximum margin hyperplane that perfectly separates the data points of different classes without any misclassification. Soft margin. When data points outliers is not perfectly separable, SVM uses the soft margin technique. This method introduces a slack variable for each data point to allow some misclassifications while balancing between maximizing the margin and minimizing the violations. Kernel. It is a mathematical function used in SVM to map input data into higher dimensional feature space. C. The C parameter in SVM is a regularization parameter that balances margin maximization and the penalty for misclassifications. A higher C value imposes a stricter penalty for margin violations, leading to a smaller margin but fewer misclassifications. The mathematical background of the SVM is as follows. The data points are represented x1, x2, x3 and so on up to xn. Below is the diagram which shows the data points. Some data points are in red color, some data points are in orange color. So orange color represents the negative points and red color indicates positive points. These two data points are separated by a line that is called hyperplane, and the dotted blue color indicates the getters both are positive as well as negative. For each data points, that is x, here x is a point. It is not a x coordinate, it is x is a point. and each points has weightages. The weightages are represented W1, W2, W3 and so on up to Wn. After calculating W1, W2, W3 and so on Wn, we sum up all the W values represented as W bar and bias. B is the bias value. Output is Y. The final equation is Y is equal to W bar into X bar. It is a dot product plus B. The equation for the linear hyperplane can be written as W bar dot product X bar plus B equal to 0, where W is the direction perpendicular to the hyperplane. Here you can see the diagram. This is the W bar. And B is offset or distance of the hyperplane from the origin along the normal vector W. Mod W is the Euclidean norm of the weight vector W. Here, the graphical representation of the data points with W and hyperplane. If the value W bar into X bar plus B greater than or equal to 0, then it is classified as positive. And if the value is less than or equal to 0, it is negative. The objective function needs to be optimized subjected to yi of W into X plus B greater than or equal to 1. In mathematical optimization, the method of Lagrange's multiplier is a strategy for finding the local maxima and minima of a function subjected to a equality constraints. The Lagrange's multiplier L is equal to, the equation is represented here, half of W bar dot product of W bar minus sigma alpha I into yi W bar xi plus b minus 1. Here in this, we need to find out W bar as well as alpha values. Now, to find out alpha values, we need to take the derivative of Lagrange multiplier with respect to W bar as well as B. After taking the partial differentiation, then we'll arrive W bar is equal to sigma alpha I yi xi bar. Similarly, if you take the partial differentiation with respect to B, then we'll arrive sigma alpha I xi is equal to, if you take the partial derivative of Lagrange multiplier with respect to B, then we'll arrive sigma alpha I yi equal to 0. So substitute these partial differential terms. That means this W bar and this sigma alpha I yi terms in the above equation L, and upon simplification, then we'll arrive L is equal to sigma alpha I minus half of sigma I sigma j alpha j yi yj xi bar and xj bar. So this is the main equation for finding out the hyperplane. We'll solve one example with the data x1 bar is equal to 1 1, x2 bar 2 2, x3 bar 5 6, x4 bar 7 4. The data points x1 bar and x2 bar on the negative side and x3 bar, x4 bar are on the positive side of the hyperplane. Now we need to determine the hyperplane, that is support vector regression. Now this is the equation to be used for finding out the support vector regression. First we need to determine xi bar dot product of xj bar and yi yj. So here this is the these are the values for xi bar and xj bar and yi yj. Upon simplification, then we'll arrive the Lagrange multiplier x is equal to alpha terms minus half of uh, sigma of alpha terms, y terms and x bar terms. Now we take the partial differentiation with respect to alpha 1, alpha 2, alpha 3 and alpha 4 to obtain the equations in terms of alpha 1, 2, 3, 4. So these are the partial differentiations. with respect to alpha 1, 2, 3, 4. Then after arriving the equations, we solve the linear equations to arrive alpha 1, 2, 3, and 4. So after arriving the values, alpha 1 is equal to 1, alpha 2 is equal to 1, alpha 3 is equal to minus 9 divided by 22, alpha 4 is equal to minus 3 divided by 22. After obtaining the alpha values, substitute the alpha values in this equation. W bar is equal to sigma I is equal to 1 to n alpha I yi xi bar. So after simplification, then we'll arrive W bar is equal to minus 12 comma minus 12. So this is what is the W value. Then we need to calculate the B value. B is equal to half of minimum of W bar into Xi bar. That is when Yi is equal to plus 1 plus maximum of W bar into Xi bar Yi on minus 1 side. One is positive 1, the other one is negative 1. So after simplification, then we'll arrive B is equal to 90. So these are the two output parameters W bar as well as B. The SVM classifier function f of x is equal to W bar into x bar plus B. For maximal hyperplane, f of x is equal to 0. So that means W bar into x bar plus B is equal to 0. So after simplification, that means after substituting a W bar and B, then we'll arrive the equation that is x1 plus x2 minus 7.5 is equal to 0. So this is what is the equation of the hyperplane. Thank you. Jai Hind.